In this lesson, we'll learn about the domain of a function, how to calculate it, and how to express it. The domain of a function is a set of all values of x for which the function is defined. The range is a set of all y values corresponding to these x values in the domain. So suppose we want to write the domain and range for the following relations where we have x-y pairs where y is a function of x. So looking at this first example here, the domain is the set of all the input values or x values. So I have -1, 0, 3, 5, and 2. So I can say that the domain is the set of those 5 numbers. Now you can write them in whatever order you want. I'm going to just write them in the order that they appear left to right here. -1, 0, 3, 5, and 2. So the domain is specifically those 5 numbers. The range, similarly, is the set of the 5 y values. Now, you'll notice that there are not 5 different numbers. 2 appears twice. You don't need to write that twice. When you're listing what the range is, you're listing what all the possible values are. So when I write that the range consists of the numbers 0, 2, I don't have to write 2 again because they've already included that, -7, and 5, that covers all the possible output values or y values in that relationship. In the second example, again, my domain is the set of all the x values, 0, 1, 2, 3, 5, and 10. And the range is the set of all the y values. Now, most of these y values are the same. 2, 2, 2, 2, 2, and finally 5. So I only have to list 2 and 5. There are only 2 different y values or output values for this function. In this third example, my domain is the set of the numbers 0, 1, 2, 1, and 9. I don't have to write 1 twice, so 0, 1, 2, and 9. And if I look at this, notice that this 1 appeared twice. Say 1 corresponds with 5 and 1 also corresponds with 4. I can write the domain and range of this relationship, but let me just point out, although I can describe this, let's say the y values are 1, 5, 4, -4, and 10. In this example, there is a relationship between the x and the y. I can talk about the domain and the range, but this third example here does not represent a function where y is a function of x. We can still talk about the domain and range, but just realize that this is not a function relationship here. Even if we didn't have the pairs written, we would probably know that because there are only 4 elements in the domain and 5 elements in the range. So at least one of the domain elements has to be paired up with 2 range elements for that to be possible. So this is not a function relationship, but there still is a domain and a range. Now, looking at function rules and determining the domain. When we're looking at the domain, again, we're looking for all the x values for which the output is defined. The first example here, we have a linear function. Y equals, or f of x equals, 5x plus 1. That's a linear function. No matter what number I substitute in for x, I'll get a value for y that makes perfectly good sense. The domain for this particular function is all real numbers. Now, interval notation, this is the left to right, thinking about a number line. What sort of x values are possible? Well, anything from all the way at the left, -infinity, through all the way at the right, +infinity. So again, remember with interval notation, we're writing not an ordered pair, but from the lowest to the highest continual interval of x values that are possible. So if there were gaps in the middle, we'd have to write more than one sequence like this to cover the possible domain. Now, the second example, y squared equals 5x squared minus 3. This expression, this here, if I solve for y, I'd have y equals plus or minus the square root of 5x squared minus 3. This is an example of something where y is not a function of x. In this case, we'll skip over writing the domain and range of this non-function relationship. But we'll have some more practice with finding function domains that look similar to that in just a moment. Y is not a function of x in this case, so we'll skip this one. In the last example here, we have y equals the square root of 4x minus 9. There's a linear expression in this expression here in the function rule, but it's under a square root sign. So in order for the output value to be defined, something that we can graph is what we're interested in, I need to make sure that I'm not going to end up with imaginary solutions. Or in other words, I need to make sure that 4x minus 9 is greater than or equal to 0. That way I can take the square root of this and have a real number output for y. So if I solve this inequality here, I can determine what sorts of values for x we need, and then we can write that into interval notation. So just solving this, add 9 to both sides. 4x would have to be greater than or equal to 9. So x would need to be greater than or equal to 9/4, which means that in interval notation, 9/4 is the smallest number in my domain, and I can go as large as I want. Now, in the previous example, we had parentheses around both ends. Parentheses mean the up to but not including. Infinity can never be included because it's the largest number possible, or the concept possible. When I have an or equal to sort of inequality, I'm going to use square brackets to indicate the end of the interval. So I've got a square bracket at the low end of this interval at 9/4, and then up through infinity, with parentheses always around either infinity or negative infinity using this interval notation. Now, some more practice writing interval notation for domain. This time we have 3 different rational functions. With rational functions, one of the things we have to make sure is that the denominator is not 0. So if I have a denominator of 0, a fraction will be undefined. But this function, otherwise the numerator is linear, the denominator is quadratic. Those are both perfectly well defined for all values of x on their own. It's just that I don't want x squared minus 9 to equal 0. So if I figure out what values of x make x squared minus 9 equal 0, well, that would be either x equal to positive or negative 3. Those are the things that we can't have. So my domain in this case is everything except for positive and negative 3. Now in interval notation, that might be easier to see what these intervals are, thinking about a number line. Here, let's say I've got 0, 3 is over here, negative 3 is over there. It's okay for me to have anything down this way, anything between 3 and negative 3, or anything above positive 3. I just can't have those two individual numbers, either x equal to negative 3 or x equal to positive 3. So I'll write 3 intervals as my domain. The leftmost interval, this one here, goes from the left, the lowest number, negative infinity, up through but not including negative 3. The second interval we've got here is between negative 3 and positive 3. Now, in order for me to say I want both of these intervals to be part of my domain, I'm going to use a union symbol. This means the interval from negative infinity to negative 3, and also another interval from negative 3 to 3, and yet again another interval from the other side of positive 3 up through infinity. That's my third interval there. So there's 3 separate intervals around and between the 2 excluded domain values 3 and negative 3. Now, looking at the second example here, this will be somewhat similar. I can see in this denominator it's a little bit harder to determine when that's equal to 0 because it's a higher degree polynomial, but it's factorable. It's cubic. I can factor out an x and have x squared plus 4 remaining. And that denominator is what I don't want to equal 0. So I don't want x times x squared plus 4 to equal 0. Now x squared plus 4 is a prime polynomial. It can't be factored any farther. So I'm just going to use zero product property and say that, well, I don't want either of these to equal 0. So I'm writing non-equalities as opposed to the usual equals 0. X squared plus 4 can't equal 0. Notice if you try to solve this second factor, I'm going to get x squared shouldn't equal negative 4. And taking square roots, we'd only get imaginary solutions. So I don't really have to worry about this. I'm not worrying about x being imaginary numbers. We're looking for what are all the real number values of x that we're allowed to use, or conversely, thinking about what are the values of x, the real values of x that we're trying to exclude. Well, we're trying to exclude 0. There are no other real number values of x that need to be excluded here, because nothing else would make this fraction undefined. So my domain is everything except for x equal to 0. So again, maybe to think of this on a number line, well, 0, I want everything except for that. So the things to the left of 0, which go down to negative infinity, and the things to the right of 0, which go up to positive infinity. So that's two intervals, negative infinity through 0, not including 0, along with things starting at the right of 0 up to positive infinity. So my domain is the union of those two intervals. Now this last function here is not precisely a rational function because I've got a non-polynomial in the denominator. But again, the numerator will be fine for any values of x. The denominator, it's a denominator, so I need to make sure it's not equal to 0. But notice there's also a square root. So I also can't have square roots of negatives. So I know that x plus 5, the stuff under the square root sign, the radicand, x plus 5 shouldn't be negative. It also shouldn't be 0. So if it shouldn't be negative or 0, that means it has to be greater than 0. That's the only options left. This x plus 5 must be something positive in order for this fraction to be something we can evaluate. So that's easy enough to solve. Subtract 5 from both sides, and we get x is greater than negative 5, which means, number line-wise, negative 5. I'm good for everything above negative 5, nothing down below, so just one interval for our domain. Negative 5 through infinity. Not including negative 5, it's a strictly greater than. If x were equal to negative 5, in this example, that denominator would be the square root of 0, which is a 0 denominator, and that's not good. Now, one last set of examples. We're going to use a different notation this time to write out the domains. We're going to use set builder notation. So instead of thinking about intervals, we'll just think about what values of x we need to exclude, or what values of x we need to include, whichever is easier to write. So, for instance, in this first function, f of x equals x plus 3 over x squared plus 9. We've got polynomial over polynomial. Polynomials are defined for all real numbers. I just need to make sure that this denominator isn't 0. Now it's x squared plus 9 that I don't want to equal 0. Notice that's never going to be the case with real numbers for x. I could rearrange this and say x squared can't be negative 9, or x can't be plus or minus 3i. But we're interested in the real number values of x. There are no real number values of x that are going to be excluded. So in terms of our domain, it's going to be all real numbers. In set notation, that's the set of all values of x such that x is a real number. So there are lots of different notations, but this kind of fancy R there means all real numbers, or the set of real numbers. In other words, anything you want from the set of real numbers is allowed for x in this case. Now in the second example, this denominator should look familiar. This is the denominator that factors as x times x squared, this time minus 4. And I don't want that denominator to equal 0. This could be factored x minus 2, x plus 2, since it's a difference of squares. I don't want that denominator to equal 0, so that means that none of the factors can equal 0, or using zero product property and avoiding all of those possible options, I know that x shouldn't equal 0, x shouldn't equal 2, and x shouldn't equal -2. Any one of those three values would cause the denominator in this second example to equal 0. Now, x equal to 2 would also cause the numerator to equal 0. That doesn't change the fact that we don't want x to equal 2. It's still not in the domain. So our domain is the set of all x values such that x is not equal to, and we have three values to include here, 0, 2, or -2. Sometimes you'll also see that written with the not equal sign several times. X is not equal to 0, x is not equal to 2, x is not equal to -2. You'll see that written either way. Now in this third example, I've got f of x is equal to the square root of 4 over x minus 3. So I've got a square root and I've got a denominator. Again, the two things I need to worry about are make sure that the denominator isn't 0 and make sure that the expression under the square root sign, the radicand, is, since it's a square root, it can't be negative. So 4 over x minus 3 has to be positive. So in terms of the denominator not equaling 0, since it's a nice simple denominator, I can see that x should not equal 3. Now in order for the fraction 4 over x minus 3 to be positive, for a fraction to be positive, you either have to have a positive over a positive or a negative over a negative. I know that the top here is positive, so what I'd need is for x minus 3 to be positive as well. So that would mean x has to be greater than 3 if I solve that inequality there. So x isn't equal to 3 according to the first half of what we discussed, and then we found out that x should be greater than 3. So I can write my domain. I don't want x to be 3, but I don't have to say that if I just say x must be greater than 3. So the set of all x values such that x is greater than 3. And that's our domain. So you may now continue on to your study plan and work towards earning your mastery points.